He probably has the
You
same
should
one.
go first.
Yeah, okay, so it's number 4 on the homework assignment.
Okay.
It's on the phasor diagrams, and we did a little bit on phasor diagrams, but I was
Uh-huh.
just wondering whether it's as simple as
Yes,
getting, okay.
it's as simple as that.
So it's just getting the amplitude and the phase associated with the,
Yeah, I mean, you can pull the phase off of here.
yeah, and the amplitude as well.
Yeah.
Okay.
Well,
Or
well, I mean, the amplitudes are all the same, right?
for A, B, C, and D?
Well, no, so
Okay, sorry.
so you have 4 slits, right?
Mhm.
Because looking at this, there's 2 side lobes, therefore there's 4 slits. Oh, and I guess I tell you there's 4 slits.
Yeah.
Okay, so when you write down the fields for each of, or for light coming through each of the 4 slits at some point in the observation plane, the amplitudes are going to be the same for all of them.
Oh. So like, how does that relate to the points on that you're talking about with A, B, C, and D on the main lobe?
So if you look at C, for example,
Yeah.
that's with the phase change of pi halves, I mean, phase difference of pi halves.
Okay.
So you'd start off and you have U1 is that, 2 is whatever we called it, U3 is A e to B minus J, 2 delta phi, U4 is A e minus 3 J delta phi. So this one, phase is 0, so that means we just go out some distance A.
Yep.
And here, for point C, this is pi halves,
Yeah.
so, you know, pi halves.
And then A would be, and then you just go to.
Okay, that's all this. And then you see, where do you end up? You know, what's the vector sum? What does it add to?
Okay. That makes sense. All right.
Yeah. Okay. All right, so we're good? Yeah.
I did have a question. Last class, we talked about how there can be total transmission through the dielectric
Mhm.
if the phase delay is
Mm-hmm.
a certain multiple of 2 pi. How does that relate to, say, something like the
So
Brewster angle? Because I know that
it
it's
doesn't.
angled, not at all. So it's another
It's
technique.
just on top of the Brewster angle.
Okay.
So this shows what is happening with a single interface. And it's basically R12 or R21.
Wow.
And so whatever that is, that factors into the expression for R12 pi.
Okay.
So, yeah.
Thanks.
Okay. All right, other questions? Okay. All right, so last time, did we start with the finishing up the end slit?
You ended up with the Ness.
Well, yeah, but we started the lecture, I think, with the end slit.
Yeah.
And then we talked about the dielectric slab. And then we started on Fabry-Parots. And a Fabry-Parot is pretty simple in that it's just 2 reflective surfaces that are parallel. And if this distance is fixed, you can call it an etalon. If it's movable, you can never call it an etalon. But you can call it Fabry-Parot. So what we want to do today is look at some consequences of all this stuff. And at the end of last class, we had plotted the transmission, and you recall that the transmission properties of Fabry-Parot are the same as for a dielectric slab, except we replaced R12 with the square root of the reflectance. So in other words, the same equation holds for a Fabry-Parot. And then we looked at this and said this is m times 2 pi, this is m plus 1 times 2 pi. And we said here that we have some full width half max. And then we saw that full width half max, because the coefficient of finesse is generally large, we can approximate this as 4 over the square root of the coefficient of finesse, instead of that arc sine expression we had. And then the coefficient of finesse is equal to 4 times the reflectance over 1 minus the reflectance quantity squared. Okay. So we made the comment that as the reflectance goes up, approaches 1, denominator, of course, gets small, which means coefficient of finesse gets big.
A quick question. Last lecture, you wrote down the finesse as like some fancy TypeScript
Yes.
F when you defined it. In the delta full with half mass, half whatever. Anyways, is that F that finesse value, or is it?
It's the coefficient of finesse.
So it is that.
Yes.
Okay, because you also
So-
define. Oh wait, it's
and
the
so-
coefficient of finesse, not finesse itself.
Yes.
Okay. Okay. Good.
And so the finesse then is equal to the separation, which clearly is 2 pi in units of delta, divided by the width of a peak. And so that then is pi over 2 square root of the coefficient of finesse. So that's one definition for the finesse. And so typical values of the finesse, maybe 30. That's a pretty easy value to hit. You can get up to maybe 1,000. You work really hard at it. You can spend a lot of money.
So intuitively, the finesse, that's how tight those peaks are?
Yeah, it's the separation divided by the width.
Okay.
So one way to think about it is how many widths fit in that separation.
Okay.
And that's going to have a really specific meaning in just a few minutes. So by knowing the finesse for Fabry-Parot, that tells you almost everything you want to know. Okay, but we haven't gotten there quite
And
yet.
it's all just a result of the reflectance?
Mhm. Yeah.
Okay.
I'll go back to reflectance. Okay. Yeah, and you could say to yourself, well, gee, if I have a cavity, meaning 2 reflective surfaces, as the coefficient of finesse gets bigger, it requires the reflectance to increase. Reflectance maxes out at 1. So what if you had a reflectance of, say, 99%? Well, then the moment you turn on some light to go into the Fabry-Parot, initially, 99% of it gets reflected, right? Only 1% goes in. But that 1%, 99% of it gets reflected here and here, and meanwhile you're dumping in 1%. And so over time you build up the power that you have in here until you reach steady state. So there's a transient regime and there's a steady state regime. And then all of this is for the steady state regime. But clearly, as you increase the reflectance, that increases the amount of time it takes to reach steady state. But fortunately, light is really fast. And these tend to be pretty small. So it all happens really fast. Okay, so one thing that one could do is make a Fabry-Parot modulator. And if we were to do that, we could take these 2 reflective surfaces, and delta, which is the phase difference, is equal to what again?
And
4 pi over lambda naught.
N.
N2. And N2 is what? It's the refractive index of whatever's between the mirrors. And then D, separation of the mirrors times cosine of theta 2. Theta 2 is the angle between the mirrors that the light propagates. Okay, so if we set theta 1 equal to theta 2 equal to 0 degrees, then the cosine is just 1. And so we have delta is 4 pi over lambda naught into d. And if I've got light going in here, and I look at the transmitted light as a function of delta, then we just have this sort of thing, right? And so let's say that I set everything up so I'm sitting right here. So I've got maximum transmission through this Fabry-Parot. What can I do to the Fabry-Parot to make me fall off of that peak?
You can change any of those things.
Yeah, change any of these three things that it's dependent upon. And usually if you're trying to modulate something, you're not going to change its wavelength. So fix the wavelength, that gives you two choices. You can change the refractive index of what's in there, or you can change the separation. Changing the separation is pretty easy. It's not necessarily fast, but it's easy. Changing the refractive index, you have to have an electro-optic material. So if you make this an electro-optic material and put mirrors on either side of the electro-optic material, then you've got an electro-optic modulator, meaning a Fabry-Parot electro-optic modulator. And then whatever the time constant is of applying a voltage, that's pretty much your response time of the modulator. And so you basically start off here, apply some voltage, end up over here. So as you apply the voltage, you fall off the peak, turn off the voltage, you go back up. And so then you can have voltage as a function of time, and then transmission as a function of time basically tracks, this voltage. So that would be one way of making a modulator, a very fast modulator. Now, another way you could do it is we haven't talked about anything other than a dielectric material in here, but we could put in a material that is has some absorption. Specifically, if we had a material in here that, say, with no applied voltage was very transparent, but when we apply a voltage it becomes absorptive, then what happens? In this property, or response of the Fabry-Parot is due to light bouncing around in here, right?
So that would just go flat, right?
Yeah, if you make this absorptive, then you kill the bounces. And if you kill the bounces, then what happens? You don't have multiple beam interference anymore, so you don't have multiple beam interference effects. So if you made this absorptive, if you could turn on and off the absorption. Whenever you turn on the absorption, you kill the transmission. So it turns out that's easy to do. Gallium arsenide, some epitaxial layers, make it so that the epitaxial layers form the mirrors and the conductive material in between the layers. When you pass a current through it, it becomes absorptive. When there's no current, it's not absorptive. So that becomes a very easy way to make a modulator, a semiconductor Fabry-Parot modulator. Okay, any questions?
What was that chemical called? You said that material?
Gallium arsenide. Or it could be indium phosphide or gallium nitride, whatever.
This seems very familiar, like in silicon waveguides, they would apply a heater to the waveguide. But in this case, is light would be traversing versus going inside the waveguide?
Yeah, so with the waveguide, silicon waveguide, usually what you'll do to make a modulator is you'll have a Mach Zehnder. And then you'll put a
Yeah.
heater on one side. And so pass a current through here, do some joule heating, heats this up, changes the refractive index.
Phase, yeah.
Now this is different propagation time than that, so difference in phase, and then you can kill the interference.
So this is just a completely different device then?
Yep. Yeah, so this is basically a two-beam interference device. This is a multiple beam interference device. And two-beam interference device, what does it look like as a function of phase difference? It's always sinusoidal.
And then adding more and more squishes it around.
Yep. And so to go from a peak to a null, you've got a lot more phase difference you need to add in. Whereas with something like a Fabry-Parot, where you're using interference of lots of beams, then you don't have to have much phase difference to kill it.
Oh, so it's real easy to modulate fast.
Yeah. Yeah, they're really fast. Yeah. So it comes down to what the time constant of the electrical drive circuit is to how fast it is.
Because we were told, this comes from 562, Dr. Camacho, that these modulators you can probably modulate up to like 50 gigahertz or something
Yeah,
like
you
that.
can.
So how about, like, for these guys?
Gets back to what your electrical circuit time constant is.
Oh, okay.
Yeah, so I mean, you can definitely do 50 gigahertz. You can do more. I mean, you start to have to work at it pretty hard, just because you're at such high frequency.
Yeah.
Yeah. And usually here, you wouldn't use a heater to do it. You do, I mean, the best thing is to get a refractive index change going. So, if you cause some current to flow through the waveguide, then you get an absorption going, which in a Mach Zehnder, that's not really what you want. In Fabry-Parot, that can be quite effective. So, but yeah, you can do things really fast.
Another question. This looks like, this finesse idea looks very much like the Q idea in circuits.
Oh, yeah.
In circuits.
Yeah, it's quite related to Q.
Everything from bandwidth over.
Yep. Yeah, Q is the bandwidth divided by the base frequency.
Yes.
And here finesse is separation of peaks divided by the bandwidth. Okay. Now let's shift gears a little bit, but still stick with Fabry-Parots. And let's look at Fabry-Parot spectroscopy. Which historically has been a really critical analysis method for measuring wavelength and relative wavelength. Now, we talked before about this situation where we had a Fabry-Parot in between two lenses and a monochromatic extended source and sort of a 2F imaging system. And we looked at what the interference pattern would be on that screen. And it's basically a series of concentric circles. And then if we start in the middle and go out radially, we have something that looks like this. And I'm just going to plot this in terms of delta. If it was radius, then it wouldn't be uniform. It'd start to squish. If we apply in terms of delta, then it'll be uniform. So this is for a particular wavelength, call it lambda 1. So this is the delta for lambda 1, meaning this is 4 pi over lambda 1 into d cosine theta 2. Now, if we had some other wavelength, lambda 2, emitted by the point sources, then we would get a similar sort of ring pattern, but it wouldn't be the same ring pattern because lambda is different. So it would be, something else, shifted a bit. And so the question becomes, how small of a delta lambda can we measure by looking at that set of rings, one from each wavelength? And if I plot on top of this what the second wavelength does, it's basically something like this. And the question is, how close can these two things be before we can't resolve it anymore? We could call this delta for fun. Yeah, Carlos?
So I'm a little lost, and I think because I forgot the definition of the delta. So that's the phase difference, right? Is that what we're saying delta is?
It's the phase difference between adjacent rays.
And so,
when we're looking at the dielectric slab, then basically it's the phase difference between the two adjacent rays.
correct, but we're talking about more than just two, right?
Yeah, well,
So
and then,
there's-
so here if the phase is 0, here it's delta, the next one it's 2 delta, the next one's 3 delta,
Okay, and so they're all just
and delta.
pretty much the same phase difference, just a multiple of them or whatever between each other. Okay. And so here, when you say that you're doing two lambdas, are you saying that you're doing lambda 1 and lambda 2? Both lights would be emitted at the same time, just different wavelengths.
Yep. Yeah, and then we're plotting on the delta scale for just one of them.
Just for one.
Yeah, which means that the other delta, we're basically doing a lambda 1 over lambda 2 scaling of the other thing to be able to plot on the same axis.
Okay.
Yeah.
I get it. Sorry.
Yeah, no, good questions. So, the question is, how close can these two peaks become until we can't resolve?
Half power.
Yeah, that would make sense. In fact, we had an expression for that. Delta full width half max, which was about 4 over the square root of the coefficient of finesse. That seems pretty reasonable, right? Well, it turns out that, just to make life more difficult, there's another criteria that gets used. So, that other criteria is called the Rayleigh criterion. And in that case, what we do is the two peaks together will do something like this. I mean, that's what you'll actually measure. And so if we normalize it to call this 1, then the Rayleigh criteria says that when this is 8 over pi squared, that's the best we can do. So if this little dip is more than 8 over pi squared, we say we can't resolve it. If it's 8 over pi squared or less, then we say we can resolve those two peaks and realize that we have two peaks. Okay, so this would be, say, delta A, and this would be delta B. And so delta delta is that difference. So we could use that criteria and go through all the math and calculate what delta delta is. And it turns out what we would get is 4.2 over the square root of the coefficient of finesse. I don't want to do all the algebra. I just wanted to draw your attention to the fact that, yeah, why don't we just start with full with half max? It's the same thing, essentially, within 5%.
So that's saying that we do a little bit better than full with half max,
That we can do
or
a little bit worse than full with half max.
yeah. Oh, sorry. When I meant better, I meant maybe a little bit further apart.
Yeah. Yeah. But basically, it just says, hey, if you're within a full with half max of for the two peaks, you can't tell you have two peaks. It just washes together, and it just looks like one peak. That's the bottom line. Okay, so kind of interesting, but what really matters is, okay, so delta delta, whether you use the Rayleigh criterion or full with half max, we essentially the same thing. The question is, what delta lambda does that correspond to? And rather than calculating a delta lambda, instead we define something called a chromatic resolving power. And the chromatic resolving power, we'll write as a script R, we'll define as the wavelength, the basic wavelength, divided by the minimum resolvable wavelength difference. And if we go through all of the algebra, it turns out that's about equal to the finesse times 2 times N2D over lambda naught. Now, this N2D, what is that? Refractive index times the distance between the mirrors, which is the optical distance between the mirrors. So optical, or rather refractive index times physical length is an optical path length. So that's the optical distance. The 2 means a round trip. And divided by lambda naught, what does that mean?
Dividing the space back and forth into how many wavelengths?
Yeah. So that term multiplying the finesse is basically how many wavelengths long is a round trip. Now, if it's 2 wavelengths long, well, that's a pretty small cavity. If it's 20,000 wavelengths long, well, that's something microscopic. Okay.
Is there any meaning to the 3 lines in your equal sign on the outline?
Yeah, that's defined as. Yeah. Yep. Okay. So let's do an example. Let's say that lambda naught is 500 nanometers. So kind of blue-green. And let's say that N2D is 10 millimeters. So, something macroscopic, just a centimeter. Not too big, but not too small. And let's say that the reflectance is 90%. So again, not crazy, it's very readily achievable. Then the finesse is pi halves square root of the coefficient of finesse. And that would give pi halves square root of 4r over 1 minus r, quantity squared. That's just the coefficient of finesse. And so we end up with pi square root of the reflectance, 1 minus the reflectance. And it turns out that that is 29.8, or about 30 for these parameters. Yeah.
Is that meant to be 4R squared?
No.
I have several places in the notes where I wrote down 4R squared.
I don't think so, but I would have to go back and double check. But I'm pretty sure this is correct. Okay, so then 2 into d over lambda naught. So that's going to be what, 20 millimeters over 5 times 10 to the minus 3 millimeters, is that right? No, it's 10 to the minus 4 millimeters. Right? Or wrong. If I'm wrong, let me know. Okay, so this is 4 times 10 to the 5. I think I'm off by 1 order of magnitude.
Yeah, I think it's, I typed in -5.
Because that's 7, right? And it's
Yeah.
I know.
Oh, okay.
It's a 500, so it's 2.
500 nanometers. It's 5 times 10 to the minus 4 millimeters.
Yeah, 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 correct.
Okay. Oh, but that should be 4. Because 20 divided by 5 is 4. Yeah. Okay. Good. So that means we've got 30 times 40,000. So that means the chromatic resolving power is 1.2 times 10 to the 6. So it's over 1 million. So think about what that means in terms of this definition. The minimum wavelength difference we can resolve is 1/1,000,000th of the wavelength. That's awesome. That is extraordinarily precise. And this is with kind of a crappy Fabry-Parot. It's only 90% reflectance.
So what would be the
Yeah.
point?
Can you say that statement again about the what that means?
So this means that we can measure a wavelength difference that's 1/1,000,000th of the actual wavelength.
Oh, okay.
Yeah, it's pretty wild.
Yeah.
Mark?
So then what would be the point of getting a Fabry-Parot that's better than that, than getting the 1,000?
Yeah, I mean, kind of depends on what you need.
Yeah.
But yeah, here, for most things that we're interested in, that's probably really good.
Yeah.
Yeah. So in other words,
That D is, okay, you just make them larger,
yeah, you can make it bigger.
bigger to get better resolving power.
Yeah, yeah, absolutely. Yeah, there's a lot of room for increasing the resolving power by increasing this and increasing that. Yeah. But even just with these simple parameters that aren't hard to hit, wow, we have exquisite sensitivity in wavelength measurement resolution, which is pretty wild. So way back when quantum mechanics was being developed, and there was a lot of experimental work looking at gas spectroscopy, so the emission lines of different gas molecules, and to look at the molecules or the atoms in different states. It turns out that they would emit light frequencies that were just minutely different. And Fabry-Parots were how you would measure those differences. And that's how quantum theory was validated, is using Fabry-Parot spectroscopy, because you have such precise resolving power.
And then validated just because they could show that there was variation.
Well, they could actually measure what the difference was as a function of whatever was being done to the atoms. And it tracked exactly what quantum theory said. So that was useful.
So can this only measure super tiny differences?
We're about to finish the story, yeah. Yeah, we'll get there. Which brings us back to finesse, and why finesse is so important. Okay, so we could also look at the minimum resolvable frequency difference, translate the wavelength difference into a frequency difference. And if we do that, it turns out it's equal to speed of light in vacuum divided by the finesse times 2 times N2D. And for this particular example, we find that the minimum frequency difference is 500 megahertz, which compared to 600 terahertz is really good. So again, it's a millionth of the base frequency. Okay, so now let's go back over here, and let's say that we take this wavelength lambda 2 and somehow we change it just a little bit. We make it just a little bit bigger. Then what's going to happen to the ring pattern?
A little fatter.
Fatter like this?
Yeah.
Turns out not. If I change the wavelength,
So then we get something like the Riley criteria.
yeah, so if I change the wavelength and make it more different from the other wavelength, what happens to that peak?
Yeah.
Yeah, it starts moving, right? Starts moving out. So this ring pattern starts to expand. Or if we take the radial cut here, what happens is this moves over, right? And then if I change it even more, it moves more, right? And if I keep changing it, eventually I'm going to get to right here. I'm back to the original situation.
Can you repeat that one more time?
What's that?
Could you repeat that one more time?
So if I take the blue peaks and I start moving them, then the blue peaks repeat.
That's right.
Eventually, I'm going to get back to the original situation. And I won't be able to tell that that's different than the original situation.
Seems to be really close already.
Yeah, so you have to be really close already in order to get that resolving power. So, the question is, how close do you have to be? Well, the separation between peaks, we call that the free spectral range. And the wavelength difference that corresponds to the free spectral range is about lambda naught squared over 2 times N2D. And for frequency, the free spectral range is about C over 2N2D. Okay. So if we go back to our example over here, and we look at the free spectral range and calculate it, it turns out we'll end up with 0.125 angstroms.
That's small.
That's really small. So we can get this great chromatic resolving power only within a really small range of wavelengths. Okay. So if I plot the transmitted power is a function of wavelength, then basically what I'm saying is we have this. The separation in wavelength is delta lambda free spectral range. And then here, the width is delta lambda min. Okay, so if we think back to the definition of the finesse, what's the definition of the finesse?
How many wavelengths? How many?
It's the separation between peaks divided by the peak width.
How many peaks do we-
So the separation between peaks is delta lambda, free spectral range, and then the peak width is just delta lambda min. So in other words, the finesse tells me how many peak widths I can fit in between adjacent peaks. And if my finesse is 30, then that means I basically have 30 resolvable wavelengths. Yeah.
As the wavelength changes, doesn't the total distance between each of those interference increase?
Not really. I mean,
Instead of just moving, doesn't it also kind of expand?
yeah, it will, but if you're looking at just adjacent peaks, that is so small in comparison to the move that you can neglect it.
Okay, because I remember doing the radar class, you kind of learned where you look at multiple peaks,
Mhm.
then you can kind of increase your free spectral range because the difference between multiple peaks only works for a particular
Mhm.
difference in frequency.
Yeah.
Is that the technique that's kind of used here at all, or is it
I
just?
don't know if it's ever used in optics. It might be, but I don't know. Question. But this is the thing I want you to remember, is free spectral range tells you how many resolvable wavelengths you have between peaks.
Let me make sure I'm reading your rating rate. That's delta lambda free spectral range over delta lambda min.
Mm-hmm.
And where did we define delta lambda min?
So that's basically the delta lambda that corresponds to that delta delta.
Okay.
Yeah.
Can I just restate something
Yeah.
to make sure I understand it? So your free spectral range tells you the distance between your peaks, right? Between-
Yes. Uh-huh.
So that number, the meaning of that 1.25 angstroms is just saying, doesn't matter that how good it doesn't matter that we have a R of 1.2 times 10 to the 6, because if we change our wavelength too much, it would just start repeating and we can't really,
We can't resolve that.
okay.
Yeah, it's like
So
having
we
a,
have to stay within that 1.25 angstroms, or else it doesn't matter anyways.
exactly.
Okay.
It's like a 2 pi redundancy in a periodic system. You can't resolve multiples of 2 pi. Yeah.
I just want to make sure I'm reading it right. Delta lambda free spectral range is equal to lambda naught squared.
Uh-huh.
Okay.
So is there some value that tells us, well, it's a good thing, do they put specs on it, like saying, they tell us, let's say they give us the R value.
Mm-hmm.
Our I value looks amazing. Is there a value that compares the R to the free spectral range?
No, usually you'll just get the free spectral range.
Okay.
Yeah.
Because that's the one.
So when you get a Fabry-Parot, you'll see the free spectral range, and you'll see chromatic result.
Because you can just assume that the R value is amazing.
Yeah, I mean, well, you'll get free spectral range, and often you'll get the chromatic result.
Oh, you will?
Yeah. And then from that, you can easily calculate delta lambda. Yeah. Okay. So, any other questions on this? Okay, so now, let's spend some time on application now. So spectroscopy is definitely an application. there's another name for this kind of spectroscopy, and that is creating an optical spectrum analyzer. So if you have, say, a laser source, the laser source is by its nature narrowband, quasi-monochromatic, but it's not monochromatic. So if you want to know what the spectrum of the laser is, what do? Well, you need to be able to resolve wavelength very precisely, but not over a very big range, because it's quasi-monochromatic. So you create an optical spectrum analyzer, and one way of doing the optical spectrum analyzer is to just have a Fabry-Parot and stick one of the mirrors on a piezo mount so that you can modulate it back and forth. So that means you are changing that distance d between the mirrors. And so what does that mean? Well, if we plot this in terms of wavelength, the transmission, so I'm going to change from I transmitted to just transmission, and transmission is just I transmitted versus I naught, basically. Then for the mirror in a certain position, what will happen is it will have the usual Fabry-Parot peaks, right? And then as I change the mirror position, what happens to these peaks is measured on a wavelength scale. Yeah, they move. So by changing the mirror position, I basically can change these and move them. So if I have some spectrum that I want to measure, then I can take this narrow peak and scan it across there and measure that spectrum. It's actually the convolution of this passband M spectrum. But as long as this is narrow compared to that, then it's more or less the spectrum. Does that make sense?
Can you walk through that one more time?
Sure. So if you look at this particular position, how much power gets transmitted? It's basically this times that, and then integrate the area of the result. And then as you move this over, it's intersecting more of the area of that curve. So when you do that integral, you have more power, etc., until you scan across the whole thing. So as a function of wavelength, then measuring power or measuring signal on your electric detector, on your photodetector here, you'll get something that looks like this.
Yeah. Is that basically, we're using those peaks almost as like delta sampling functions?
Yes. And that's exactly it.
It's like a convolution.
It's a convolution. Yeah.
So, okay, so is the peaks themselves that end up attenuating through the source, or like?
No, these stay constant,
Those stay constant?
and you're just moving them. You're just scanning them across the source spectrum and measuring the result on the photodetector.
So in practicality, how wide of a spectrum could we analyze this? A few
Whatever-
nanometers, tens of nanometers?
Whatever the free spectral range is of the Fabry-Parot.
Yeah.
Okay, so we have room to find that.
Yep. Yep. Because if you had a Fabry-Parot with a free spectral range that looked like, with a transmission spectrum that looked like this, say, well, that's a problem.
We couldn't get the whole thing, but we get a high resolution.
Yeah, Yeah, which wouldn't matter because we can't get the whole thing. Yeah. Okay, so do you kind of see how the game is played? You want to measure some spectrum that's narrow. You use a Fabry-Parot that has a significantly narrower passband, but a free spectral range that is broad enough that you only get one peak that passes over that spectrum. That makes sense? Okay. Okay, so then we can look at another application of this. Let's say that you had an argon ion laser. Then, yeah, they're very cool. So you have an argon ion laser. You basically have this gas tube. And then you have some electrodes in here. And you put a high voltage across that. And inside that tube you've got argon gas. And the voltage is high enough that you break down the argon gas to create argon ions. So you have free electrons and argon ions. So now this is conductive. So you're passing a current through the resultant plasma. Okay, and it turns out that if you do that right, then the gas becomes an optical gain medium. So you get stimulated emission. If you can create a cavity, how would you create a cavity? Well, you just need mirrors. So call it R1, call it R2. And then you want this thing to laze in a single polarization state. So how you cap off the ends of the tube is really important. If you just put a window here at normal instance, there's nothing about the setup that prefers one polarization state over another, so you'll have unpolarized light coming out of the laser, which is usually not what you want. But if you take this and mount a window so that you're at the Brewster angle coming in on this, what happens to the Brewster angle?
Total transmission.
For
TM.
for TM. So TM would be in this direction, right? So that passes through with no attenuation here. But what about TE? You get a little bit of reflection. Where does it reflect? Well, the little bit of reflection comes off like this. But it turns out that that's basically an excess loss for the TE compared to the TM. And any little bit of excess loss usually means whatever has the excess loss is not going to win. And whatever doesn't have the loss will win, and it'll just take all the power. So that means you end up with polarization in the plane of the board, i.e. TM polarization, with respect to the windows. Which also is why you always want to have the cover on the laser when it's lasing, because you've still got reflections here, and they can blind your eye. You don't want to catch them in the eye. Unless you're feeling adventuresome and defeat the interlocks and keep the cover off, which sometimes you have to do when you're debugging one of these things. Okay, but at any rate, so that's the tube, and then you have the mirrors here. Now, the mirrors, let's just say they have the same reflectivity. So what would you call that pair of mirrors?
We're still a Fabry-Parot.
It's a Fabry-Parot, right? So a laser cavity is a Fabry-Parot cavity. Okay, so let's see what that means. Let's plot as a function of wavelength. Let's plot the gain. as a function of wavelength for this argon ion gas, then it'll be something. Let's say it looks like this. Okay, so that means one would think that any wavelength in that range, if we can get it going here, it will laze. But there's another factor, and that is the loss. Let's say that this is the cavity loss. So only wavelengths that have net gain will laze. So that means between here and here, because those have net gain. All right, so are we good with that? Okay, now, the two mirrors comprise a Fabry-Parot. So, if I plot on this axis the transmission of the Fabry-Parot, what does it look like?
Look like the same thing, but,
Yeah, just be the spiky thing, right?
yeah.
Okay, so let's do that. That'll be something like this. Okay, so the question is, what's the spectrum of the light that comes out of that laser?
Should be green in between, like inside of the peaks of the
That's the convolution.
Well, this is the actual set of peaks corresponding to the Fabry-Parot. And that actually means you have an integer number of wavelengths between the two mirrors. And if you don't have an integer number of wavelengths between the two mirrors, then it turns out you're not going to laze because you don't keep the phase relationship up. So basically, you can only laze in these wavelength bands.
So will you laze in all of them?
Ah, yeah, so that's the question. Does this have net gain? Yeah. Does that have net gain? Yeah. All these have net gain. This one doesn't have net gain. That doesn't have net gain. So what you get is basically a spectrum that looks like this. Yeah, something like that.
That's one of the reasons why lasers aren't fun.
So then if you design your Fabry-Parot such that your free spectral range was wide enough, you could get a monochromatic, right? Because only one of those peaks would land in the...
Yeah, you're absolutely right. So, and in practice, what does that mean we'd have to do here? What's that?
Make it bigger.
Less separation.
Less.
So we'd have to take our mirrors and bring them closer together. But we have a problem. That's going to shrink the volume of our optical gain medium. And then we won't have as much optical gain, so we can't get as much power out. So if we want a high power laser, we cannot do that. Although in principle it works. So if we just want to laze at one of these Fabry-Parot peaks, what do?
Another Fabry-Parot,
Another Fabry-Parot. How big does it have to be?
big enough to just pick out the peak and then...
Yeah, it needs to be quite a bit smaller, right? And if we take that Fabry-Parot and stick it on the outside, then basically we're going to take that spectrum, run it through the Fabry-Parot, and select, just a single one of these peaks if my free spectral range is big enough. But that means I'm throwing away all this power. So instead of sticking the Fabry-Parot outside the laser, let's stick it inside the laser. So now we've got a Fabry-Parot inside the laser, and I guess I should do a different color. So we basically have something that looks like this. And now that Fabry-Parot introduces loss here where there's no transmission, and no loss or very little loss where it does have transmission. So that means now this laser line, or rather laser mode, is the only one that has net gain. So we're going to laser only in that one. And then we can get coherence lengths of, say, 100 meters. Whereas if we were operating without that etalon at all these different lines, so we have the spectrum, then maybe our coherence length is, I don't know, 50 centimeters or something. So if we want really long coherence lengths, we know we have to have very narrow spectrum. To get it out of the gas laser, where these mirrors are kind of wide compared to, because we need a bigger gain medium to get enough power, then we have to throw another Fabry-Parot in the cavity to put in this additional filtering.
So is that done?
Oh yeah.
So there's monochromatic laser?
Well, okay, so that kind of gets us into terminology. This,
Oh, because that's a little band too.
yeah, this right here is called single line operation. And then this here
That's a quasi-sterilized.
is called single mode operation. Because it's a single longitudinal mode of the laser. Each one of these is a different longitudinal mode. And I can explain single line in just a minute. Okay, but if you just throw a Fabry-Parot in here, how likely are you to have its transmission peak line up with one of the peaks of the cavity?
Say it's a toss-up unless you have something to tweak it.
Yeah, it's pretty much not. It's not going to line up. So you have to be able to make this adjustable to take this passband and center it over a mode. So how do you make it adjustable? Could do piezo, but that's pretty hard inside of a laser cavity. Instead, and the other thing is the laser cavity, it doesn't have to be fast. You use a piezo for speed. So you take all of this and you basically stick it in a heater. Because refractive index is a function of temperature. And the separation is a function of temperature. So by tuning the temperature of this thing, you can take this transmission peak and tune it across the spectrum. And then how do you know when you've got it right? Well, over here, you have an optical spectrum analyzer, which is another Fabry-Parot. And you run it, the output of it, into an oscilloscope. And basically, what you do is you toggle that mirror with the voltage for the piezo. You do it fast. And so you're taking your optical spectrum analyzer peak and you're traversing across this, flying back, traverse across, fly back. In other words, you feed it a sawtooth wave. And then you can actually see the spectrum as a signal on your oscilloscope face. And then as you dial your temperature, you can see this thing scanning out the Fabry-Parot peaks. And you dial your temperature until you get this one centered over the biggest peak, and now you've just maximized your laser power.
So if our two Fabry-Parots don't agree and the peaks don't overlap,
Mhm.
do we get no output out of the laser?
Very little. Yeah, almost nothing. Yeah. And your optical spectrum analyzer will show you that.
So in your oscilloscope, you'd see nothing, or you'd see something very little.
Yeah, you'd see, if this is your screen, you'd see something, maybe something like that. Yeah.
And so when you're right on top of it, you just see that big spike.
Yeah, when you're right on top of it, comes along, see that. If you're off a little bit, come along, see that. Then you turn up the heat, you see, nothing, and then suddenly you see this guy, turn up the heat some more. Suddenly you see that guy, this is the only signal you see. And you just sweep through them until you're starting to fall off on the other side, and then you come back to whatever your max is. And that's how you tune. It's all just Fabry-Parots within Fabry-Parots analyzed by Fabry-Parots. And if you understand what the transmission of a Fabry-Parot is like, it's not a big deal.
You have to have pretty precise control of that heater.
Oh, yeah. Yeah.
And you even have to, in theory, also cooling it, because the laser's gonna be heating it up, right? As it's
Yeah.
gaining across it.
Yeah. Yeah, so you could use a thermoelectric cooler. Yeah, and so usually what you want to do is either raise the temperature, and so then you have to have some kind of a heat sink for the excess temperature or heat to flow into, or you could cool the item, the Fabry-Parot. And now basically whatever heat is coming in from the laser, you're sinking it into your thermoelectric cooler. And then by changing the voltage on the thermoelectric cooler, you change how much heat you're sinking, and then you control the temperature. Yeah.
So these aren't like the $3 laser you buy at the shop, are they?
Yeah, 30 years ago, you'd spend $100K on a laser like this. Yeah.
How big is this, like, roughly, you know,
Yeah, it's big. Yeah. Yeah, now, it turns out that if you look at the argon ion spectrum, then you've got gain here at 514 nanometers. You've got some gain at 488 nanometers. And then there's some gain at some other things. I think 353 nanometers in the UV. And then there's a really strong peak at, 1,049 nanometers, something like that. And so if you just take the laser and create this plasma, you have gain at all of these things. And so normally what you do is you stick a prism here, so the light goes this way, and then you have a mirror that you rotate to pick one of those lines. So if you get an argon ion laser, you can operate at 514 nanometers, you can operate at 48, you might be able to operate some of the other lines. So that's why this is called single line, is meaning it's operating at one of the gain lines of the argon ion laser. And then you stick your Fabry-Parot in here for doing the single mode operation. And so any gas laser, this is pretty much what you can do. Helium cadmium, helium neon, then there were others. Okay, so have you had enough Fabry-Parots?
No way.
So if I did the high cost, last question about Fabry-Parots.
Yeah. Okay, well, that's it for today. Next time what we'll do is get started on thin films. And based on what we've already learned, thin films
Okay, question, single mode again is, so a single line still then has some spectrum, right?
Yes.
Single mode. Now that, for me, mode and waveguides is, is
So
different.
this is a single